This is the section 2.1 video lesson. So remember, you've got to make sure to watch these because these are lessons that I will not be covering in class due to the fact that they're kind of the easier lessons where you can technically just read about it in the textbook and learn it on your own, but I still feel like I want to be able to tell you about it. So make sure you watch all 4 of them for this chapter. Alright, so chapter 2 is called Matter and Change. So we're going to go into matter, we're going to talk about how it changes through physical changes, chemical changes, that type of thing. So a lot of chapter 2 should actually be reviewed from physical science that you either already had in high school or even from physical science that you had in middle school. So section 2.1 is properties of matter. So just a reminder from chapter 1, matter is anything that has mass and takes up space. Okay, so as we discussed in the chapter 1 video, you're matter, you have mass, you take up space. You know, a book bag is matter, a pencil is matter. We discussed how even though air doesn't seem like it's matter, air does take up space and have mass. Okay, that's why when you blow up a balloon, it expands because it's taking up space. And we can feel air pressure changes, which means it has mass. So, but we talked about how things like light, which is a form of energy, would not be considered matter. So all matter consists of tiny particles called atoms. So any type of matter that we talk about this year is made of atoms. And we'll of course learn about the different types of atoms from the periodic table, but every form of matter is made of atoms. So that's why it has mass and takes up space, because atoms, they each have their own mass. So, the definition of matter is anything that has mass and takes up space, which of course is volume. So anything that has mass and volume. So let's define those 2 terms just to make sure you know what they are. So the mass of an object is the measure of the amount of matter in the object. Okay, so I know it's kind of weird because the definition for matter has the word mass in it, and the definition for mass has matter in it. Okay, so matter is anything that has mass and takes up space. Mass is the amount of matter an object contains. And then of course volume is the amount of space occupied by an object. So the larger the object, the larger the volume because it occupies more space. So there are a couple of different types of properties we're going to talk about in this chapter, and we're going to start with the difference in an extensive and an intensive property. Okay, so an extensive property is a property that depends on the amount of matter in a sample. And examples are mass and volume. Okay, so extensive, we care how much we have. So in my 2 pictures, here we have a cup of water. Here we have a whole swimming pool of water. So let's look. Would they have the same mass? Obviously not. This swimming pool is going to have a whole lot more water, a larger amount of water. So the mass will be larger. Are they going to have the same volume? Do they take up the same amount of space? A cup of water in a swimming pool? No, because again, the amount of water is different. So extensive properties depend on how much of the substance you have. It's going to change if I have more or less of a substance. So like I said, mass and volume change as we have more and less of something. Like in our pictures, the cup of water versus the swimming pool of water. So now let's look at intensive. So an intensive property is a property that depends on the type of matter, not the amount. So intensive, we don't care how much we have, we just care what it is. Okay, so examples are density and hardness. So let's do hardness because density, I know some of y'all probably don't remember what that is yet, so we'll go over that in chapter 3. Alright, so here we have some aluminum rods, and here we have paraffin wax, which is just candle wax. Okay, so are they going to be of the same hardness? Of course not. The aluminum is going to be much harder than candle wax. I can take my fingernail and scrape away candle wax. I can't do that with an aluminum rod. Okay, so they have a different hardness because they're 2 different things. This is aluminum and this is candle wax, 2 totally different substances. Okay, and so what I want you to see is it doesn't matter what size the candle is. I could have one of those little tiny tea light candles. I could have a big giant one like this. The wax is still going to be of the same softness. Okay, I know we said hardness, but let's face it, we all know wax is not very hard, it's soft. So it doesn't matter how large the candle is, I'm still going to be able to scrape the wax with my fingernail on any size candle because the size of it doesn't change the consistency of that wax. Okay, so extensive depends on how much you have. Intensive, we just care what we have. All right, so let's move on. You're going to hear me talk about substances a lot in class. Okay, so a substance is a type of matter with a uniform composition. Uniform just means it's the same throughout, because we're going to talk a little bit later about mixtures, and they do not have a uniform composition. So it's the same throughout. Examples include water and gold. Now, the problem is, I do have to specify, because in real life, most of the water that you're around is not pure. Okay, you know, water in the ocean has all kinds of stuff in it. You know, lake water, streams, even your drinking water. I know you want to pretend like that's pure, but your drinking water is not pure. There's lots of dissolved compounds in there. If you've ever heard the term hard water, that means you have more dissolved compounds than most people. If you've ever, if you have a glass shower door and you don't clean it for a while, you'll see kind of that white film get on it. Those are all the dissolved compounds that were in your water. Okay, so even our drinking water is not pure. But you can have pure water if you distill it. And then gold, same thing. Most of the gold we're around is a mixture, because even though we like to wear gold as jewelry, it's actually kind of a soft metal. So it bends easily. So like if I have gold rings and I'm sitting here banging my hand on the chalk, the expo marker tray all the time, I'm gonna get lots of dents in my ring. So a lot of times it'll be an alloy. That's why you can see the different carats of gold when you go to a jewelry store, like 24 versus, you know, maybe only 18 karat. That's showing how much gold you have versus other metals. All right, so substances are pure. They're uniform throughout. A lot of times they'll be called a pure substance because they're the same throughout. So let's talk about physical properties, and then we'll get to physical changes. So physical properties are characteristics of a substance that can be observed without the substance undergoing a change in composition. Okay, so physical is all about keeping the same composition. So examples would be boiling point and color. All right, can I look at this? This is a piece of sulfur, by the way. Can I look at this and tell you the color without, you know, having to set it on fire or put it through a reaction? Yeah, we just look at it. Okay, so that is an example of physical property. This sulfur is yellow. We just looked at it, said it was yellow, and that's it. We didn't have to do anything to it to figure out that it was yellow. Okay, so physical properties, again, can be observed without changing the composition. Now, physical change, on the other hand, involves a change. Like the difference in physical property and physical change is a property is just kind of a descriptive characteristic of a substance. Whereas a change, we're actually doing something to the substance. But in a physical change, we're changing some of the properties, but we don't change the overall composition. So we are changing something about it, but it has to remain the same substance. Okay, and so examples are like melting and cutting. So ice is made of what? Water. Well, when it melts, what do we get? Water. Well, what is the chemical formula for water? Okay, even though you haven't been in my class very long, you should know that. Okay, water is H2O. So the ice is made of H2O. The water is also made of H2O. It's just gone from the solid form to the liquid form. Okay, a lot of people want to say, well, it is changing because it's going from ice to water. But remember, ice and water are the same thing. They're both H2O. So we're changing something about it. We're changing the state of matter, but the substance is actually the same thing. It's still water. All right, cutting is another example. If I have a piece of paper and I cut it, it's still paper. It doesn't change what it is. It's just smaller pieces of paper. So a lot of times physical changes, they change kind of the way it looks, but not really what it is. So physical changes can be reversible or irreversible. So if I get this ice out and it melts, could I put it back in the freezer and refreeze it? Yes. So that would be an example of a reversible change. However, some are irreversible. Okay, if I cut this paper, there's no way without added resources that I could put it back together. Now, yes, I know I could tape it or staple it or glue it or recycle it, but all of those are needing additional resources like the tape, the glue, the staples. We can't just magically put it back together and it become whole again. Okay, so physical changes, like I said, can be reversible like the melting, where we can just refreeze it, or irreversible like the cutting of paper, or like cutting hair. Okay, if I cut hair You know, I can't just magically reattach it. I have to like tie each strand or glue it or something. I can't make it just one piece of hair again. All right, so let's move on. Let's talk about something I'm sure you've learned about a million times in your schooling career, and that is the states of matter. Okay, so there's 4 states of matter: solid, liquid, gas, and plasma. All right, so a solid is a state of matter that has a definite shape and volume. So a solid, if you put it in a new container, it doesn't change shape, it doesn't change volume or size. It just stays the same shape, goes into the new container, that's it. All right, the particles of a solid look something like this. They're very orderly, like you see how they're in like perfect rows here, and they're very close together. Notice you can see no space in between them. But are they moving? Now I know it might be hard for you to see on the video because I don't know how good a quality this is going to turn out. But if you look at it real closely, you can see that they're just kind of vibrating a little bit in their fixed locations. But the particles themselves never trade places. Okay, so particles of a solid, they are moving, they just vibrate in their fixed locations. Okay, they don't go past one another like other states of matter. Because the particles are so close together, solids are not easily compressed. Compressed is when you take something and squeeze it into a smaller area. Okay, you can't do that with a solid. Like if I get a rock, I can't be like, oh, I want to make it smaller and squeeze it real hard and make it smaller. Okay, so solid, like I said, definite shape and volume, can't be compressed, but the particles are moving. They're vibrating in their fixed location. Vibration is a form of movement. All right, so let's look at liquids. So liquids, they have a definite volume, but they will take the shape of their container. Okay, so if I have a 20-ounce Coke and an empty 2-liter bottle, if I pour the 20-ounce Coke in the 2-liter bottle, it's going to reshape to take the shape of the 2-liter bottle, but will it fill to expand to the 2-liter bottle? No. Now, would that could be convenient if it did? Of course, because then you could just keep filling a larger and larger container and it keep expanding. But that's not what happens. Okay, it'll just settle in the bottom. It's not going to expand to fill. All right, liquids, the particles kind of look like this. So again, do you see a lot of space in between them? No. So they're pretty close together. But unlike a solid where they vibrate in their fixed locations, liquids, they can kind of move past one another. It's called flowing. They can flow. That's why you can like pour a liquid, whereas a solid, they'll just kind of fall in. Liquids, you know, they flow in nicely. But again, because those particles are so close together, liquids are still not easily compressed. That's why if you have a large water bottle and you don't really want to carry it around, you can't just squeeze it into a small one and carry that instead, because liquids are not easily compressed either. All right, so definite volume that takes the shape of the container. And of course, again, not easily compressed because those particles are so close together. All right, so let's talk about a gas. A gas has no fixed volume or shape. Okay, so in class, I'll be showing you an example of a gas because everyone's seen a solid and a liquid and have all kinds of experience with those. The problem is when I talk about gas, a lot of you, yeah, you've learned about them over the years, but no one ever shows you like, oh, this is how you pour a gas. This is how a gas takes the, you know, shape and size of its container. Most people don't show you that. So in class, I'll be showing you that. All right, so if I have a small container of gas and I put it in a large container, it's going to take the shape, but it's also going to expand to fill the container. Okay, it doesn't matter what size it is. It will spread out until it fills the whole container. And so again, I will show you this in class, so you don't just have to take my word for it, like you'll be able to see it yourself. Now, gas particles look kind of like this. If you look, there's a lot of empty space. They're moving very fast and they're very spread out. Okay, so remember, solids, they're kind of vibrating in their fixed locations. They are moving, but they can't really move past one another. Liquids, they're still really close. They're moving faster and they can pass one another. They can flow, but remember, they're still real close together. Gases, they're just like all over the place. Okay, super spread out, moving very fast. And so as you can imagine, can I take these particles and squeeze them a little bit closer? Yes. So gases can be compressed. That's how scuba divers have such small tanks. We'll wait on the announcements.
We need the following teachers to please report to the Media Center: Ms. Ferguson, Ms. Stubbs, Ms. Schwartz, and Mr. Carr. Once again, we need the following teachers to please report to the Media Center:
I'm sorry.
Ms. Ferguson, Ms. Stubbs, Ms. Schwartz, and Mr. Carr.
Okay, just keep in mind, y'all, that's gonna happen through like every video I ever make. Alright, so let's talk real quick about the scuba divers. Alright, that's how they can have such small tanks, is they take a bunch of oxygen and compress it into a smaller area. And so then they can breathe it for long periods of time. Alright, so there is a difference in a vapor and a gas. Alright, so a vapor is a gaseous state of a substance that's normally a solid or liquid at room temperature. So for example, what is water at room temperature? It's a liquid. So if I boil it, it becomes water vapor because I had to do something to turn it into a gas. Whereas, for example, oxygen, what is that normally? Well, right now we're breathing it in, it's normally a gas. Okay, so since oxygen's already a gas by itself, just at room temperature, it's called oxygen gas. Steam, which is us boiling water, because we had to do something to turn it into a gas, is called a vapor. Okay, so oxygen gas, water vapor. Okay, that's the only difference in a gas and a vapor. Vapor, we usually have to do something to get it to become a gas. All right, so let's move on. So here's just a picture to remind you of what they look like. Okay, so see, solid is not going to take the shape of the container. See, it didn't fill in this kind of triangular type shape at the bottom. It did not expand to fill the container. Notice the particles, they're very orderly, very close, but are they moving? Yes, they're vibrating in their fixed locations. Liquids, notice it did take the shape of the container, but it did not expand to fill the container. The particles, they are more random than a solid. They aren't in these nice fixed locations. They can move past one another, but again, see, they're very close together still. So there's not much room for compression. And then a gas, I know it's kind of hard to see, they made it really light. It took the shape and it filled the entire container. The particles, they're moving very fast, they're very far apart, so I am able to actually compress them closer together. All right, so let's look at our last one, and that's plasma. Okay, so a plasma is an ionized gas-like phase consisting of electrons and positive ions. So what happens in plasmas a lot of times is they're superheated, and so eventually the electrons separate from the rest of the atom. And so if you lose negatives, what are you left with? Positives. Okay, so what you end up with is positive ions and then electrons that are separated and floating around. Okay, so where can you find plasma? Well, stars, like our sun and other stars in the solar system, are plasma. The aurora borealis, the northern lights, those are examples of plasma. All right, so plasma, like I said, electrons have just separated from the atom. Not all of them, some of the electrons. So you're left with the positives and the negatives. They're still far apart, like a gas. Like notice this picture is similar to a gas. But instead of having neutral atoms, you have the positives and the negatives. All right, so let's look at this section assessment. So it says, name 2 categories used to classify properties of matter. Well, the 2 categories we talked about were extensive and intensive. Okay, remember, extensive depended on the amount, intensive depended on the type. Okay, so we have extensive and intensive. All right, so extensive depended on the amount, intensive depended on the type. Number 2, explain why all samples of a given substance have the same intensive properties. Okay, so they said all samples of a given substance. So let's just pick a substance. Let's pretend like we have water. Okay, so why would all samples of water have the same intensive properties? Well, remember, intensive depends on the type of substance. So if they're all the same substance, are they going to have the same intensive properties? Yes. Okay, so samples of the same substance have the same intensive properties because, I'm just going to abbreviate this, intensive properties, IP is going to be intensive properties, because intensive properties are based on the type of substance. Okay, and like I said, IP is just intensive properties. I realized I was going to run out of room. Okay, so again, as long as it's the same thing, it's going to have the same intensive properties. Remember, extensive is the one that depends on amount. So like a cup of water and a swimming pool of water will have different extensive properties But since they're both water, they're going to have the same intensive properties. Okay? So number 3, solid, liquid, gas, and plasma. Solid, liquid, gas, and plasma. All right, number 4, describe the 2 categories used to identify physical changes. Well, remember, we said a physical change can be what or what? Reversible, like melting, or irreversible, like cutting. Okay, so we have reversible or irreversible. And like I said, the reversible would be like melting ice, because we could refreeze that. The irreversible would be like cutting paper. Because again, we cannot reattach that without using outside assistance. Alright, so I'm going to erase this and let's go ahead and move on to, I think there's 2 more questions. Alright, so in what ways are liquids and gases alike? Well, a solid, remember, particles are in those fixed positions. In liquids and gases, the particles can move past one another. Again, like I said, that's called flowing. A liquid can flow, a gas can flow. Again, I'll show you in class a gas flowing, because I know most of you have probably never seen that. All right, so both of them can flow. Or you could say both of them can take the shape of their container, because both of them do. Okay, so it doesn't matter which one you pick. Okay, I'm just going to put a little arrow right here. So we could say both can flow, okay, which means again their particles can move past one another. But like I said, you could say both can take the shape of their container. That would be a perfectly good answer also. Then the second question says, in which ways are liquids and solids different? Okay, so, well, we know liquids can flow, solids can't. We know liquids take the shape of their container, solids don't. We know liquids are random and solids are orderly. Liquids move faster, solids move slower, so you could use any of those. Okay, so I'm just going to do the liquids have random particles and solids have orderly particles. But again, any of those things I just listed you could say, because they're all differences in liquids and solids. Alright, so last one, number 6, is the freezing of mercury a reversible or irreversible physical change? Well, if I freeze mercury, could I just heat it up and melt it? Yes, I could. So since I could melt it again, that would be considered a reversible change. Alright, so that's section 2.1. Make sure you don't forget to watch the section 2.2, 3, and 4 videos also.